Hi. So now that we've talked a bit about dominance, it's time to move on and talk a bit about equilibrium as well. And part of the reason we're going to do this is because there's a lot of games where we don't have dominant strategies. And in fact, part of the real interest in game theory comes from the fact that in many cases, predicting what one player does depends on what the prediction of other players' actions are. So let's take a look at that in a little more detail. So the main concept that is used in game theory in terms of equilibrium is known as Nash equilibrium. And the idea behind the concept is basically that it's a set of strategies or actions by the players such that if each player correctly predicted what other players were going to do, then they would not want to change their action. So they're choosing the best possible action that they can in response to what the other players are doing. It's very stable. So the nice things about equilibrium, it's a stable point, so that if we reach a point like that, then nobody wants to change. Nobody regrets the strategy that they played. So if you actually go through this, they're doing the best they can. They couldn't have done better. So it has some nice properties. Now the name Nash equilibrium comes from John Nash, who was the person who actually proved the first general existence theorem about equilibrium. We'll come to that a little bit later. It's also sometimes called Cournot-Nash equilibrium, and that's because Cournot in the 1830s was actually studying oligopolies, so studying different numbers of firms competing in markets, and was studying more or less this kind of equilibrium concept, and so it's sometimes called also Cournot-Nash equilibrium. It's also sometimes called equilibrium just in short, so we'll use different terms. Now, in thinking about the reasoning behind it, it's a very important issue is how we justify equilibrium. And let me give you one equilibrium justification that actually you can trace back into Nash's dissertation. It's not so much that equilibrium points are stable that makes them great predictions, as much as the fact that non-equilibrium points are unstable makes them not great predictions. So predicting a non-equilibrium point requires that somehow you believe that somebody's going to do something that they were going to regret or are not doing their best response. So this isn't necessarily a justification for equilibrium, but a strike against non-equilibrium. More generally, there's a very long and active area of game theory, which is questions of when do players reach equilibria, how do they come to equilibria, what kinds of conditions on their knowledge or the dynamics or some sort of evolutionary process, what pushes people towards equilibrium and away from non-equilibrium points. So under what circumstances can we justify this as a solution concept, under which circumstances might it be questionable. There's experimental, empirical, theoretical analyses of these. So there's a very large literature on this subject. For now, what we're going to do is start by just talking through the basics of what equilibria are, and then we'll come back at different points and mention some of the other issues as they arise. Okay, in talking about Nash equilibrium, we're going to take it in various pieces. The first piece is defining what it really means for somebody to be best responding. And then, given that, we'll be able to define equilibrium in its most basic form, which is pure strategies, one where people are choosing a particular action. And then afterwards, we'll talk about situations where we might have to have some randomization in order to have predictions of equilibria. And finally, then we'll talk about existence of equilibria. So we'll take each one of these in turn. And let's start by talking about what a best response is. So in terms of our normal form notation, we start with a game of set of players, their actions, a sub i's for each I, their utility functions or payoff functions, the use of i's. And what we can do is then define a best response for a given player to actions of another player. So we say that AI is a best response to A minus I, and A minus I, when we put a minus I, that means a list of the strategies of every player except for I. So AI is a best response to some actions A minus I if the payoff to I, UI of AI against A minus I, is greater than or equal to what they would get from some alternative A prime I if they played that instead against the strategies of others. So best response is defined for a particular player relative to a set of actions held fixed for the other players. What's the best that they can do? Okay. So one thing to note here is in any finite game, it's clear that you're always going to have a best response, so you can just look at each particular action and see which one does best. Right? So let's go back to the predator-prey game that we looked at before, and then we can look at the actual actions of the prey. And so here we see, in the case where the predator is active, then we had payoffs of either -1 versus -0.8. So the best response for the prey, if the predator is active, is that the prey should also be active. So we have a best response of active for the prey against active for the predator. Now instead, if we change what the predator is doing, so instead we say that the predator is going to be passive, then we're looking at -0.7 from being active, 0 from being passive. So now passive becomes a best response. So the best response of what the prey wants to do is dependent upon what the predator is doing. So we can't define a best response without actually talking through what the other player is doing. So for each set of strategies for the other players, we can then define a best response for a given player. Now with best responses in hand, we can define what a pure strategy equilibrium is. So a Nash equilibrium in pure strategies is going to be a profile of strategies, so a list of what action each particular player is choosing, A1 through AN, that is a best response for each player against all the others. So what we need is simultaneously we've got a best response. Each person is choosing an AI such that their AI is better than the payoff they would get from any alternative A prime I, and this has to hold for each player and each possible strategy they can have, and it's holding for the set of actions that we're considering as the equilibrium point. So each player has to be best responding to the actions of the other players held fixed, and this has to be going on simultaneously for all the players. Okay, so that's the definition of Nash equilibrium. Now it's important here to emphasize the difference between Nash equilibrium and dominant strategies. So when we looked through Nash equilibrium, when we're talking about best responses, we're looking at something where we're holding fixed the A minus I of the other players, whereas when we're talking about dominance, we want a particular action to be best no matter what the other players are doing. So it has to be true for all of the alternative strategies of the other players. So dominant strategy was one that was, you didn't really have to worry about what anyone else was doing. You had something that was clearly best. That's not true in our predator-prey game, where we saw that the prey's reaction depended on what the predator was doing.